Hello, my name is Walter Unglaub, and this is which of Kepler's laws of planetary motion is a consequence of the conservation of angular momentum? The answer is the second law of planetary motion. And Kepler's second law of planetary motion can be described as a line joining a star and its orbiting planet sweeps out equal areas in equal time intervals. So what does this mean? Well, let's draw a little diagram. We have a star and a planet that orbits this star in an elliptical fashion. And Kepler's second law of planetary motion means that if you draw a line between the star and the planet in this orbit, and you let some time pass, so some time interval delta t, the planet will orbit around the star, and this line will sweep out an area. And the angle between these two lines is given by theta, and so you can write down a mathematical formula or equation that describes this type of planetary motion and this law. So if this area is equal to A, we have the change in this area A over time, dA dt, is going to be equal to r squared over 2, where r is the distance, times the change in the angle with respect to time. So if this is a constant, c, that means that as this planet orbits closer and closer to the star, it'll speed up here. So the change in this angle will be very fast. That means that if this whole thing is a constant, if this increases, then this distance must decrease. And we see that indeed this distance is smaller than this distance. This is due to a conservation of angular momentum, which according to Noether's theorem arises from this symmetry, this angular symmetry. So this is, mathematically speaking, an equivalent formula that describes Kepler's second law of orbiting planets, that this line sweeps out an area and that this area in a given amount of time is preserved, is constant. My name is Walter Unglaub, and this is which of Kepler's laws of planetary motion is a consequence of the conservation of angular momentum.